Alrighty, so before we get started with the official exam review, I just wanted to go over the basics of the exam itself. So it will be pretty much the exact same structure as the first. Everyone will have 50 multiple choice questions. They'll be extracted from a test bank, so everyone's 50 is going to be different from another's. I will post it. I will post the exam to publish the exam. My God, this Thursday, probably about the time class would normally start at 10, and you will have until Saturday at 11:59. So it's slightly different from last time, 11:59 p.m. I think last time I said you had like 48 hours until the exam was posted. But I'm gonna have it available from Thursday approximately 10ish to Saturday at 11:59 p.m. So you'll have all all of Saturday. Yeah, because technically 12 is Sunday. So yeah, you'll have all of Saturday to do it as opposed to early Saturday morning if you can't get to it before that. So yeah, so 50 questions, multiple choice. You'll have one attempt and you'll have an hour and 50 minutes, unless you require, you have accommodations, in which case you'll have the time allotted to you. But I mean, pretty much identical to the first exam, other than just having a little more time on Saturday to get it done. But that's pretty much that. Yeah, that's really all I have to say about that. Do you guys have any questions about the exam itself before we get into the content of the exam? All right. I figured pretty straightforward, pretty identical to the first time around. So this second time around should be no different in terms of that. But now let's start with the official exam review. So just like our exam review last time, although now you can't see the back of my head, but it's there. But just like last time, you guys tell me what you want me to provide examples on, explanations, whatever, based on the study guide. I don't have any plans to talk about anything specific. Rather, you guys tell me what you need, and I'll do my best. Well, I'll do my best to help you understand. And if you have more questions, please ask. Oh, gosh, excuse me. Please ask them. So I'll leave the floor to you guys. What do you need?
For me, it was like the previous assignment that we did last night. So I was a little confused for ANOVA about where to get our sample size for each group because yesterday's example was for the behavioral, the E, the C. I forgot what they abbreviated it for yesterday, but I didn't understand the difference between those sample size numbers and the big letter N.
Okay, let me pull it up so then we can all look at it. So, so here is the homework from that was due last night. Which damn, I'm so close. I was grading it before the meeting started. I have like a few more to grade. I was trying to get them all done, but I couldn't get it before we started today. But anywho, so as far as finding the individual sample sizes for each group, the behavioral, emotional, and cognitive, they're found here in the count section, in the count column. So count essentially translates, in this particular readout, it translates to sample size. So there's 21 in behavioral, 21 in emotional, 21 in cognitive. How you would, the capital N, the total number of participants, is where you would just add all of the, it highlighted everything, but it's where you would just add all of these sample sizes together. So this is just asking, this question saying, all right, how much is in each individual group? And this question is asking how many total people were in this study. So that for that, you would just add all of the sample sizes together to get the total number of people. So 21 plus 21 plus 21 is 63. There were 63 people total in this study.
Okay, that makes sense. Yeah.
Of course. And let's not forget that for the exam itself, this information will not be there. The part I highlighted, and also the likely these 2 degrees of freedom, the between and within. So part of this homework was kind of helping us to understand how to find these things. Now, granted, again, the F statistic and the P value were right there, but to calculate this F statistic, all you have to do is just take this, the MS between groups or variance between groups divided by the MS within groups or variance within groups. So if you were to take 0.587302 divided by 1.787302, it would equal 0.328597. So the equation is pretty much set up right there for you when the F statistic is not present. All righty. Oh, okay. What other questions do we have?
Hi. Can you kind of explain a little bit more the difference between the independent and dependent t-tests?
Yeah. So for independent and dependent samples t-tests, what you want to start with is to look at the samples involved. So for an independent samples t-test, imagine independent is, if you are an independent person, you're not reliant on anyone else, you're not attached to anyone else. Maybe if you're independent financially, you're not asking people for money or relying on, you get your own, you maybe you're using financial aid, but hell, you're not asking for money from your parents, or you have your own job, you're independent, you're paying your rent, you're doing this, you're doing that. Independent, you do not need anyone else. You are not reliant on any other person but yourself. Independent samples work the same way. So the samples that are in an independent samples t-test are independent of one another. They have nothing to do with the other. They don't rely on the other group at all. They have nothing to do with the other group. So an independent samples t-test would be, oh, I'm going to take a group of 7th graders and compare it to a group of 2nd graders in terms of their enjoyment of YouTube. I don't know. But I'm comparing these 2 groups of kids. Now, an independent samples t-test is saying that these 2 samples that I have, they do not contain the same people. You have your 7th graders who are approximately 12-ish years old, and you have your 2nd graders, which are approximately 8-ish years old. You can't be 12 and 8 at the same time. These 2 groups are independent of one another. There's not going to be a kid that's both in 2nd grade and in 7th grade, I would assume. So independent samples t-tests, these groups are completely separate. Dependent is a different story. So dependent samples t-test, oftentimes what we see there is it's one group of people, but instead of being tested once like they are for an independent samples t-test, they are tested twice. It's the same people. So the 2 things you're comparing for a dependent samples t-test is the same person's score, grade, rating, whatever it is you're measuring, but it's the same person tested more than once. So an example, our classic example is the pre and post test design, which is what you'll see on the GE assignment for the, I give you guys the final on the first day of class where you haven't taken statistics, or at least you haven't taken statistics with me yet. And I measure, I tally up the points, I see what exam score each individual student got on that first final exam. Then we take the class, then we take the final exam at the normal time, which is approximately, side note, about a month from now. I believe finals week is December 11th through 14th. So it's a month from today, but I digress. But I'm going to compare the first time you take the exam with the last time you take the exam. It's the same group of students, the 30 some odd of you, the 30 of you, you're the same people. It's just one group of people. But I am having it split to where I'm comparing your first exam score to your own second exam score. So if you remember when we calculated dependent samples t-test, the first thing we did once we had the data was subtract the scores from each other. I believe the example we used in class was like kids reading with a teacher present and without a teacher present. Before we started doing any part of step 3, the first thing we did was find those different scores. I'm comparing this, this group of kids, each individual kid's reading time with a teacher present and without a teacher present. It's their own scores. They're being tested twice. I'm measuring the amount of time they spent reading twice, and I'm subtracting those two things from each other before we get started with any of the other calculations for dependent samples t-tests. Same group of people, be it kids reading with or without a teacher present, or Psych 42 students taking the exam on the first day of class versus the last day of class. I still have two things that each of these groups are doing, be it the exam that the first day or the last day, or reading with or without a teacher present, but they're being tested twice. And then again, with independent samples t-test, the groups we have are completely different. So I can split the class in half. This class, let's say about 15 and 15, and say half of you get a study guide and the other half do not for the second exam. Now, obviously, that's kind of shot to shit because we all have the study guide, but just work with me here. So we have 15 people that get the final, or what am I trying to say? 15 people that get a study guide and a completely separate group of 15 not getting a study guide. Independent samples t-test, there's no crossover. No one student is both getting and not getting a study guide. Not for this example, no. So that, again, the key for an independent versus dependent samples t-test is you want to look at how the groups are split. For an independent samples t-test, the split is completely separate groups of people, separate sets, different people. They're not the same. And then for dependent, they are the same, but they're being tested twice. And that's all I have to say about that. Unless there are more questions, of course.
Can you go over the last bullet point where it talks about describing what it means for your group slash variables when you reject or retain the null?
Yeah. So when we look at any of our tests, whether it's a dependent or independent samples t-test, a NOVA, or our one sample tests, it's not enough to just know our F statistic was less than our critical value, so we retain the null. Our positive T statistic was greater than our positive T critical value, so we reject. Or it's not enough to just know when to reject or retain the null. But what I mean by kind of explaining what it means for a study is, imagine it like this. If you were to talk to your grandma, grandpa, someone who hasn't taken statistics and said, I rejected the null, Grandma, is she going to know what the hell you're talking about? No. But if you said, oh, we were comparing exam scores with and without a study guide, we rejected the null, that means that one of our groups did better. The study guide group did better on the exam than the no study guide group. Grandma's going to understand that. If you throw the T statistic at her and say, yeah, we did an independent samples t-test, the p-value is below alpha because that's the threshold of significance, and our test statistic was greater than our critical, Grandma's going to lose you. Grandma's going to be like, what the hell are you talking about? But if you say we were comparing two groups, or again, obviously each test is going to vary. With ANOVA, we have 3 groups. With one sample T or one sample Z test, we're really comparing populations there. We're using that sample to generalize to the population. But ultimately, when you retain or reject the null, what I mean is, what does that mean for your groups? What does that mean in English? Not just rejecting or retaining the null, but who were your groups? And if you retain the null, that means there's no difference. These two groups are the same. So the study guide and no study guide group did the same on the exam. There was no difference. If you rejected the null, there was a difference between the study guide and no study guide group on their exam scores. So really, that last point is just emphasizing, keep in mind that I'm not just throwing these numbers at you guys to just reject and retain, but keep in mind the context as well. What is it that you're actually doing? You're looking at a difference between this group and that one. And was there a difference? State it. Again, my example is just pretend like you're explaining it to your grandma or just someone who hasn't taken statistics. I always use my grandma because she notoriously would say that, like, oh, Angela, you like statistics? Oh, it's just like baseball. And like, yes, grandma, like statistics is great in baseball. But I think just finding batting averages and looking at that kind of stuff is a little different, as you guys know, from the statistics we've been doing in class inferentially, those dependent, independent samples t-tests. You're not going to see, they don't really broadcast that on during the World Series. Look at that p-value. But I digress entirely.
Now that you you explained that last bullet point, the second to first, so the second bullet point, it says what rejecting retaining the null hypothesis means for inferential statistics. Are you basically asking the same thing?
Yeah. So what I just mean by the inferential statistics is just all the ones that are on this exam. So that is pretty much the 2-1 sample test, be it T or Z. Spoiler alert, their conclusions are pretty much the same. They're very similar other than the standard deviation belonging to, again, population for Z or sample for T. The 1 sample tests, the dependent, independent, and ANOVA. When you reject or retain the null with any of those tests, what is that telling you? And that's going to vary from problem to problem because the situation is different from problem to problem. You know, we could be looking at, you know, chickens and how big or small the diameter of their eggs are based on eggs be big or feed me plenty. And then another question can be, hey, for a dependent samples t-test can be, hey, you know, we got this lady who drinks too much Pepsi. We're going to replace her Pepsi with water. But still, rejecting the null would say there is a difference in the amount of sleep that she got when she drank Pepsi versus water. Or there is, like, we retain the null for the chickens, so there is no difference in egg diameter between these two different feeds. It's still kind of making the same conclusion. There is a difference or there isn't a difference, but based on the problems, again, filling in those blanks is going to be a little different. For one problem, it was Pepsi versus water. The other problem was the 2 different feeds, the 2 different chicken foods. But I will focus more so on the independent and dependent samples t-test, but just kind of have an idea of what the groups are that you're looking at for all the inferential tests, and you should be okay. Go ahead. I kind of cut you off there. I just wanted to kind of put a emphasis on the end of my sentence. So go ahead, Annabelle.
Yeah, another question I had was it's step 4 we use solving the problem, and you're finding like if coincide is significant or not significant. Would you for every homework I had, it would be like this would be medium strength for our coincide, and since we reject our null hypothesis, coincide is not significant. So
My apologies. My internet connection decided to be unstable, so that's fun. I'm so sorry. Can you repeat your question?
No problem. So, for step 4, since I always write down what the problem means, I was wondering if I like was doing something wrong with our coincidence. So, like for example, I would say this would be medium strength, and since we reject the null hypothesis, coincidence is not significant. Is that right? Because I don't know if it was a correct term or not.
So when we reject the null, Cohen's d is significant. When we retain the null, it is not significant.
So rejecting null is significant. Retaining null is not significant.
That's it.
Okay, okay, thank you. I was a little confused about that part.
Yeah, of course.
To find Cohen's d for the one sample z-test and the one sample t-test, it's the same formula, right?
Pretty much. I mean, the notations are slightly different. Like for the z-test, you'll divide by the population standard deviation. And for the t-test, you'll divide by the sample standard deviation. But yeah, it's pretty much the same.
Can you also go over how to find the Cohen's d for the dependent test, please?
Yeah. So finding Cohen's d for the dependent samples t-test really sits in the first part of step 3. The first part of step 3 for dependent samples t-test is finding the mean, variance, and standard deviation of the difference scores. Again, with the dependent samples t-test, the first thing we do, we have our data set, be it, how much time kids spend reading with versus without the teacher present, or the exam scores for the first day minus the exam scores for the last day. Whatever the data is, we subtract those scores first. So for kid number 1, we take their reading time with the teacher present minus without a teacher present, and do that same thing for the remainder of the sample, the remaining kids. Once we have those difference scores, so each person should have one difference score. We're just subtracting their 2 values from each other, okay? Those different scores we're going to find the mean for and the variance and standard deviation for. So it's from that we're able to get Cohen's d. Cohen's d for dependent samples t-test is simply taking the mean of the difference scores divided by the standard deviation of the difference scores. So yeah. Did you want it? I'm explaining it, but do you want me to show you? Do you want a more specific example? What is it? I'm not sure if you need an example or an explanation here.
Can I get an example, please?
Sure.
Thank you.
Alrighty. So, let me pull it up. Actually, all right, we're gonna just make our own example. I was gonna pull up the PowerPoint, but I don't want to use the same examples that I've already used because I feel like that's kind of repetitive. All right, so let's say I'm just gonna have Excel here, our handy dandy Excel here. Let's say that we have day 1 exam score and then day 50 exam score, whatever. All right, so we have, I'm just going to make up some numbers here. Sure, good enough. And then Sure. All right. So the first thing we would need to do is find the difference scores. So with this, again, this is just kind of a makeshift example, but pretend we are doing the same example of I give you the final on day 1, then I give you the final on day 50. All right, so the first thing we got to do is take the difference scores. Now, I will say that it doesn't matter which one you subtract from the other. You can take day 50 minus day 1, or you can take day 1 minus day 50. It really doesn't matter. As long as you do the same thing for all of the participants, you're fine. So I'm going to just go this one. I'm going to do day 1 minus day 50. And I'm just going to do that for all of them. So I have my difference scores: 22 minus 99, negative 77, 25 minus 65, negative 40, 14 minus 65, da-di-da-di-da. Okay. So here are my difference scores. Now I want the mean, the variance, and the standard deviation of the difference scores. Okay. So mean is easy. I just find the average of it. Here we go. Right there. Done. We have a negative 45.4 for the mean of our difference scores. Okay. Now, we remember that the formula for the dependent samples t-test for finding variance is a little challenging, or at least we have to do a few things first. So let us do the difference squared. And then I'm going to put sum right here. So I'm going to take the sum of the difference scores first, which is just these guys. Excuse me. Oh, I know what I did. No. So sum of the difference scores, all right, negative 227. Now I'm going to square each of the difference scores and do that all the way down the board. All right. And then I'm also going to find the sum for these. All right. Now I can start by calculating the variance. So if you remember, and I can actually bring it up so we have that reference, because I don't want to just start going all willy-nilly without having any sort of context to it. Here we go. Let me see if I can pull these side by side. I can't. Okay. Wait, yes, I can. Are you guys able to see both the PowerPoint and the Excel sheet? Perfect. Okay. So, oh, God, now our faces are in the way. All right. So to find the variance of the difference scores, we need to take the sum of squares divided by the number of difference scores minus 1, where the sum of squares is Okay, so let's start with finding the sum of squares first. This is where we take the sum of the difference scores squared. So here we have that 3,400. We added all the squared scores together. Oh, look, we've done that. It's 11,983. Okay, so we're going to do 11,983 minus, now what have we got? So we have the difference scores squared. So this is negative 227 squared divided by the number of difference scores. So how many do we have here? 1, 2, 3, 4, 5. Okay. So what we're first going to do is do negative 227 squared to get that 51,529. And we're going to divide by the number of difference scores, which we calculated was 1, 2, 3, 4, 5 divided by 5. Okay. And this 10,305.8 Now this is where we're going to take 11,983 minus that. So let's do that. Oops. Okay. That's not right. What did I do? Oh, I did the wrong number. My bad. Okay. It's this number, jackass. All right. Minus, boom. All righty. So we get 1,677.2. This is our sum of squares. We did the sum of the square difference scores on the PowerPoint. It's 3,400. On our example here, it's 11,983. Minus the squared difference scores, which we have here, divided by the number of different scores. So divided by 5, there were 1, 2, 3, 4, 5 different scores. Then we subtracted that from our squared difference sum to get this guy. So the squared minus the difference scores squared divided by number of difference scores. God, it gets so wordy. But we have this. This is our sum of squares, but we are not done yet. I noticed a issue that we had for the dependent samples t-test homework is once we got to the sum of squares, we just moved forward and said that was variance. That this is not variance. This is part of it, but it's not the whole thing. We'll refer back over to our PowerPoint where now we have to take that sum of squares, which, oh yay, we just calculated, divided by the number of different scores minus 1. Again, we have 1, 2, 3, 4, 5 different scores. So to get our variance, we're going to take our sum of squares divided by 4, the number of different scores minus 1, 419.3. And to find the standard deviation, we just take the square root of our variance. Now, okay, we've done step 1 of dependent samples t-test, but that wasn't the question. The question was, hey, what the hell's Cohen's d? Well, now we have everything we need to calculate Cohen's d. So to get Cohen's d, now we just take the mean of the difference scores divided by the standard deviation of the difference scores. That gives us a Cohen's d of negative 2.22 if we were to round it. And this is a large or strong effect size. Keep in mind that just because this Cohen's d is negative, the direction of it is negative, that has no impact on the strength. So it can be a negative 2.21 or 2.22, and it's going to have the same strength as a positive 2.22, which for both cases is strong or large, whichever one you prefer. But that's how you calculate the Cohen's d for dependent samples t-tests.
Makes more sense. Thank you.
Of course. What other questions do we have? Do we have any other questions?
I have one more question.
Yeah.
The p-value, because the first bullet point says when to reject or retain the null using critical values and p-values.
Mhm.
I completely forgot what the p-value is.
Of course. So p-value is essentially the probability that the null hypothesis should be is retained. The probability that the two groups or three groups, if it's ANOVA, are the same. That p-value represents the probability that the groups are the same. Again, the null hypothesis is true, or true. It should be retained. So at a certain point, obviously we reject the null hypothesis. We say, hey, these two groups are not the same. So at what point does the p-value go from, yeah, retain, the null hypothesis is okay, they're the same, these groups are the same, there's no difference. At what point does the p-value go from there's too high of a probability that the null hypothesis should be retained to now it's too low, I'm thinking it should be rejected? That's where alpha comes in. That's our Jesus fish, our alpha set at 5% or 0.05. And when the p-value, if this is alpha, if my arm is alpha, that 5% line, if our p-value is able to limbo beneath it, it's so much easier when I can use my hands, not like my actual body, because I'm not that limber, at least not for my limbo prowess. But if alpha is our limbo bar, our p-value to be a significant limbo player, which, by the way, when you reject the null, there is statistical significance. That's why we say Cohen's d is significant when we reject the null, because there is a statistically significant difference between our groups when we reject the null. But I digress. So if you are a significant limbo person, you are a p-value. Here I am, I'm a p-value. Oh, here's my alpha set at 5%. If my p-value is 6%, 5.5%, 72%, like it was for the homework, I'm not going underneath the bar of 5%. I'm actually kind of just stepping over the damn thing and saying, screw it, I'm not screwing up my knees as a p-value that's arbitrarily subjected to start limboing. Well, when our p-value is higher than alpha, it is not significant. We are going to retain the null hypothesis. When our p-value can get underneath alpha, again, 5%, when our p-value can get underneath it, then it is a significant limbo player. People are like, damn, look at that p-value's knees. It gets super down low to the floor. Do they have apple bottom jeans? Anyway, so when your p-value is low, you reject the null. When your p-value is high, you retain it. And again, that low or high is based on alpha. If it's beneath it, at or beneath it, if it's at 5% or less, you reject the null. If your p-value is standing on top of the limbo bar, because screw limbo, if it's higher than 5%, then you would retain the null. The groups are the same.
Does what you just explained with the p-value, does that also apply to the critical values? Or is it different than that?
Critical values work a little differently. So for the critical values, that we're not really looking, we still do include alpha in our critical values, because keep in mind, when we find the critical values on our T table, on our, even our Z table technically, well, no, the Z table doesn't quite have that in there, but I digress. But we are still using alpha, but we're using alpha a little differently. Instead of comparing our p-value directly to alpha, like we do when we find significance with a p-value, for critical values, we set up what those critical statistics are based on alpha, as well as if it's a two-tailed test or not. And we also need to know what type of test we're doing, t-test or z-test or even ANOVA. But for sake of simplicity, I'm going to go with t-test here. So with t-test and with it being two-tailed, we're going to be given some values in our critical t table. And that is going to be, something like this. That's positive and negative 2.042. So for critical values, instead of thinking of it like limbo, and we have our p-value above it for retaining the null or beneath it for rejecting it, for our critical values and the test statistic, be it T or Z or F, for this pairing, now we're thinking of this as a number line. So 0 is in the middle. And we're going to plot our calculated test statistic. Again, our critical values are pointed out here at the negative and positive 2.042. So when we graph it up like this, with 0 being in the center, whatever our test statistic is, we plot it on here. So quick, someone just throw a number at me, but try not to hit my face. So what's our test statistic here? Just make up a number. Who cares?
Uh, 5.2.
All right, 5.2. Well, we have to, again, starting with 0. All right, well, it's positive. 5.2 is positive. So, all right, it's going to be somewhere over here. Well, our critical value is 2.042. So with 5.2, it's going to be past that. In fact, according to my calculations here, if I were to do this to scale at 5.2, wouldn't even be on here. But just for the sake of getting it on the damn thing, if I were to plot it on this number line, essentially, again, it's not to scale, but I don't have a paper long enough to put it there. Here's my 5.2 right there in the shaded region of my graph that I just drew, my normal distribution I drew. When our test statistic, be it T or F or even Z, if we were to plot it, when our test statistic is in this shaded area, be it over here, or if it's negative over here, we're going to reject the null hypothesis. So if it's anywhere in the shaded regions for a positive test or a negative test statistic, if it's in this shaded area, we reject it. If it's anywhere between there, in the big old white area, we're going to retain it. So if it falls anywhere, if we were to plot it, if we had a test statistic of negative 0.5, so I'll plot it. Negative, is it? Okay. Negative 0.5 is right there. We see it's in that massive white region where we retain the null. So if our test statistic was negative 0.5, we would retain the null hypothesis. If I put that on the wrong side. Oops. Here, let's pretend that's positive. And then here is our negative 0.5. All right, there we go. I got all backwards with how it's mirrored for me on here. But we have our negative 0.5, we retain it. Positive 0.5, we retain it. Positive 5.2 over here, we reject it. If we were to plot it on this number line, it's in the shaded area that is past our critical value, so we reject it. So when deciding what to do with the null hypothesis using p-values compared to alpha, we think of the limbo bar. If our p-value goes underneath it, we reject it. If it's above it, we retain it. When we're using critical values and test statistics, think of drawing out the distribution with our critical values, positive and negative, being on both ends of it, and shade the regions past those ends, just like I did here. So shading the regions past the ends that we've created, and then plot the test statistic, whatever it might be it 5.2, negative 0.5, whatever it is. If you plot it on there correctly and see, oh, it does not go past our critical value, it's in the middle, the white area, the non-shaded region, we will retain the null. If it's in the shaded region, we reject it. Right. Do we have any other questions, clarifications? How does the critical value change with different levels of significance, or can it? It most certainly can. So if you'll notice the T table in particular, we have at the top of it, in fact, here, let me, instead of just arbitrarily mentioning it, let me actually show us. So with the T table, let's go up to the top here. We have our one tail, we have our two tail. These numbers here, the 1.0, I'm looking at the two tail row to be more specific. 1.00, 0.5, 0.4, 0.3, 0.2, 0.1, da, da, da. Those all represent alpha. So typically in this class, we have gone with two-tailed test, and we pretty much set alpha up at 5%. So all of our critical values have fallen somewhere in this column when we've done t-tests, because we have a two-tailed test and alpha is set at this 5%, so it's here. But you'll see that there's a boatload of numbers in this table, and all these different columns represent alpha being set to a different level. Now, again, we haven't really used alpha set at like 1% or 20% over here. We haven't done that, but alpha does dictate critical values based on, let's say our degrees of freedom was 10, and our alpha is set at 5% for a two-tailed test. Well, it'd be 2.228. But if our alpha was set at 1% with a two-tailed test, this isn't the number we'd use. It wouldn't be 2.228. It would actually be bunk over here at 3.169 if alpha was set at 1% with a degrees of freedom of 10. But again, we typically stick with 5% for alpha for this class. But yes, alpha does certainly change critical values based on a multitude of factors, but alpha can change what your critical values are. Yeah.
Another question about the critical value that I have is for our DF. When our DF is like 178 and then it only goes to 100, would it be the one that goes to closest, or is it going to be like the next one, like 1,000?
So for our class, I would just say the closest one, which would be 100. Now, you can get more specific critical values from like t-tests online. I know you can find specific critical values, or even you can use Excel to find that. But as far as the resources I have provided you guys in this class, I've provided you with that T-table, which is from the book. So I know that T-table isn't complete as far as every single degrees of freedom being on there. So I'm willing to accept the critical value that you can find from the closest approximation to your degrees of freedom. I know it's not 100% accurate because it's, again, not the exact degrees of freedom. But granted that I have given you that particular table, I know the downfalls that come with it. I'm willing to accept them. Go for the closest one.
Thank you.
Mm-hmm.
Wait, I actually have a question related to that. So say if we have like a number that's sort of like exactly in between, say like 45 and it's like either 40 or 50, what would we where would we like lean?
So I typically tend to go for the lower one, the lower degrees of freedom personally. Again, with that one, one for the exam, with how I set it up being multiple choice and Canvas grades it, I'm not going to give you those like right in the center, oh crap, which one could it be? Because I don't physically grade those. I put the answers in the questions when I set it up for you guys so Canvas can grade it for you. But as far as those kind of like, which one is it? It's right in the middle. I'm not going to test you on that. I think for our activity, we had a degrees of freedom that was kind of smack dab in the middle. I look at all the activities. I grade them based on completion. So I have the human eye looking at that one. But I tend to go for, if I don't have the exact degrees of freedom and its critical value, That again, our table does not provide. I typically go for the lower option, but I also keep in mind that students can go with either, you mentioned 45 being between 40 and 50. I tend to keep an eye out for both the critical value for 40 and for 50, just because, just to keep an eye out. Alrighty, do we have any other questions? Alrighty, so like I said at the start of our meeting, I will post the exam this Thursday, probably about our normal class time, 10 o'clock, maybe a little earlier, maybe a little later, just depending. But certainly around that time, I will publish the exam so you guys can start taking it on Thursday. You will have until Saturday at 11:59 p.m. to complete your one attempt that has a total time limit of 1 hour and 50 minutes, unless you have accommodations that require more time. I set up that time so you can get that accommodation. Yes, we do not have class in person on Thursday, so don't go to the classroom if you're looking to go to stats, because no one's going to be there. The exam will be 50 questions, all of which will be multiple choice. Just like the first time around, it comes from a test bank, so no two tests are going to be identical. Yeah. And also, just like I did last time, I will post an announcement on Canvas saying, hey, the exam is live, just so you have that warning, that heads up. And I'll also state again, you'll have until Saturday at 11:59. I'll post an announcement saying all the same stuff again, just to kind of keep us reminded. I recorded this meeting. Hopefully, I know that my internet connection was unstable, so it kind of cut out for a second, but I did hear on my end recording in progress when I came back to the meeting. So I'm pretty sure the recording has still been going. There just might be an awkward in it, but I will post this video on Canvas once I usually download it to YouTube, and then I got to put it onto, there's a process I got to go through. So that video will be up before the end of today, but not like in 2 minutes, because it takes a while. And obviously, if my internet connection's unstable, God knows how long it'll take today. But I'll post this video on Canvas so you guys can reference it before the exam. And yeah, that's all I have for you. I will see you next Tuesday for class. So we will have class a week from today in person. Good luck on the exam. Again, I'll post it on Thursday, and I'll post an announcement saying I have posted it. There's a lot of posting. And yeah, have a good luck on the exam, and I'll see you next Tuesday. Bye, everybody.
Good day.
Look, you too. Thank you. Have a good day. Good luck on the exam and all of your classes. Make good choices.
Have a good day, Miss Cooper.
Thank you. You too.